Okay, good morning everyone, and welcome to this University of Limerick Research Week event, MACSI Assembles. I'll tell you about MACSI in a moment, but the theme of the morning is going to be collaboration between mathematics, statistics and the rest of the world. So for anyone who doesn't know me, my name is Darren O'Kiley. I'm one of the co-directors of MACSI, and my role this morning is going to be to tell you a little bit about what MACSI is, what this morning is going to look like, and then introduce our speakers. Okay, so MACSI is a group of mathematicians and statisticians who sit in the Department of Mathematics and Statistics here. And our remit really is about developing and using mathematical and statistical tools for real-world problems. And I guess one of the things that we want to share with the UL community today is that real-world problems means pretty much anything. So we have people thinking about psychology, we have people thinking about literature, we have people thinking about chemical sciences, we have people thinking about batteries, we have people thinking about metals. If you can think about it, we are interested in the mathematical or statistical element of it. So how do we work? Well, MACSI was originally founded with an SFI grant that was specifically for the purpose of mathematics for science and industry. And now, I guess, our remit has broadened and the funding mechanism has also broadened. So we have PIs with individual research grants. We are interested in plugging into European money. You'll hear some about that. And then we also are involved in various Research Ireland centres. And again, that's really about plugging into collaboration and real-world applications. So on that note, I'll tell you what's going to happen this morning. So this morning we're going to have 5 pairs of people. And you can think of this as 5 duets. So each pair is someone from MACSI and someone from outside of MACSI who have a collaboration with some specific application area, which they will tell you a little bit about. And so they'll tell you a little bit about how the collaboration works, how they talk, what they find works well, and what they find needs work in order for collaborations to work well. So on that note, I'll introduce you to our first pair. And so our first duet is going to be from David O'Sullivan and Mike Quayle. And they'll tell us about a long-term collaboration between MACSI and the Department of Psychology here in UL. So David O'Sullivan is an associate professor in statistics and data analytics in the Department of Mathematics and Statistics. His research specialties include networks, branching processes, stochastic processes, and his achievements in that area often pertain to applying those methods to thinking about social networks and how people interact. And this pairs him up nicely with Mike. Mike Quayle is a professor in the Department of Psychology, and Mike's research examines how people's attitudes change, how shared attitudes bind people into groups, and how people, in turn, shape clusters of attitudes. So what you can see already is that there's similar research interests, but framed in very different languages and mindsets. Mike has, I think, quite a long relationship with MACSI, including hiring some of our PhD graduates onto his ERC starting and consolidator grants. So I'll pass you over to the pair to tell you about their work now.
All right, thanks very much, Darren, for a very good introduction, describing my research very, very succinctly. I must keep some of those lines in my mind. So I'm just going to talk to you a little bit about some of the work that has been going on between MACSI and psychology. So Mike has been introduced, and I'm David. I'm going to start off with a little bit of about my background. So I did my undergraduate degree in UCC, and I ended up coming to University of Limerick to do an internship where I was working within MACSI on a project to predict for a specific company that manages a lot of gas users, their customers' gas demand. And I particularly like this project primarily because it was the very first time that we're using mathematics to actually solve a very specific problem. Throughout my undergraduate degree, mathematics would have been kind of like the object unto itself. We're learning a lot of mathematics for the sake of learning mathematics. But very nicely, when we came to Limerick, or came to MACSI, the problem was front and center, and all the problems MACSI seemed to work on that I was encountering was front and center, and the mathematics was in service of the actual problem. So I particularly liked that project, and ended up coming here to do my PhD, continued to do a lot of industry projects that I really enjoyed, and then my actual research interest was around network science, and part of that was building tools for computational social sciences. And so you can imagine if you were to collect a lot of data, you might want to have tools that you can analyze that data with. So for example, you might collect data around things like the Irish marriage referendum. That happened some years ago, and see how information spreads on Twitter, and you want mechanisms or tools to analyze that, and you want to see maybe what drives information to go viral, what increases its depth, and what kind of features want to characterize things that go viral or things that don't. And you might want to also understand things like the social structure that individuals divide themselves up into on these online platforms. You might want to understand, actually, if you have a left and right-leaning users, how likely is information to spread between those things like echo chambers and that kind of stuff. So when I finished my PhD on that particular topic, I did 2 postdocs, and then like a boomerang came back to the University of Limerick in 2020 as an assistant professor. And this is where I first met Mike. Well, I think it's the first time I met Mike. It's the most distinctive type of met Mike initially, where I was giving a seminar on the work I just alluded to, where I did some work around the Irish marriage referendum, where we took information about who was talking to who about the Irish marriage referendum, who was following who if they were discussing those particular topics, and to see how the extent to that to the extent to which that topic was like an echo chamber in its own right. And to do that, we had to build statistical tools to tell us how much signal was in the actual data, like so how strong was the echo chamber is, and we build tools to allow us to actually say there was an existence of an echo chamber on that particular topic. And I distinctly remember Mike sitting in the back of that seminar asking some pretty pointed questions about how the tools worked and the limitations of it and what else could you do with it. And he was clearly thinking along similar lines to what I was thinking about, but like from a very different kind of perspective, which was very interesting. And that was actually my introduction to the work that Mike was doing, and that was kind of my avenue into the DAFINET project, which actually turned out was ongoing for quite some time, and actually predating that, Mike had done a lot of work with MACSI up to that point. So Mike's going to tell you a little bit about the genesis of that particular project and where it actually came from now.
Yeah, thanks, David. So my background is that I have an arts degree, very limited training in maths, but an interest in how things fit together. And I like seeing patterns in things, but I don't have the mathematical tools to do that by myself. My main speciality is psychology, and social psychology particularly. And my main training in that is in social constructionism and language, actually. But with this interest in social interaction and social identity. And so I was doing some work breaking the rules of my discipline and trying to extend our work to beyond the methods that we had available. And I created a problem that I couldn't solve. We developed this method for collecting data from people in little interaction networks. And I naively assumed I'd just be able to use our ordinary methods on this, like linear models and regressions and ANOVAs. I was so excited at first because we got these beautiful interaction effects. And I was like, wow, this is incredible. Turned out they were entirely an artifact of a mismatch between the method and the type of data that we'd invented. And I just didn't know what to do. So almost through chance, someone introduced me to James Gleason. James, I was lucky enough that James was interested in this. And he brought 2 colleagues, Kevin Burke and a master's student who we managed to recruit into a PhD. We got funding from the IRC. And together they came in on their white horse and rescued me and developed these wonderful models for modeling this kind of data despite all the weird dependencies and assumptions embedded in this data type that emerged from the platform that we'd invented. So that resulted in some publications, but it also laid the foundation for the ideas that became my first ERC grant, my starting grant. And I've put a little image there of all the drafts that I did. And I would do a draft, and then James and Kevin would be kind enough to comment on it, and other people in MACSI, and help me develop these ideas. And that provided a foundation for this idea that I had, that we can think about attitude systems as things that bond people together in groups, that people are linked when they share an attitude, and attitudes are linked when they're held in common by people. And we can build that basic idea up into much bigger systems, which help us understand how common opinions hold groups together in society, and how this might help us understand things related to opinion dynamics like polarization and how we change society's opinions. I still feel very ignorant about the methods that we're using, but through this web of collaborations, I'm confident that things make sense and the papers that we're writing are sound. And over the years, we've built up quite a strong network of collaborations between social psychology and other social science disciplines, sociology, and people in MACSI, which have led to quite a strong body of publications and also to further proposals. So the work that came out of the ERC Starter provided the basis for the ERC Consolidator. And also one of the postdocs on the first project has put together an ERC project and got funded, also drawing on collaborations with MACSI. So I still have this vague feeling that I'm exploiting MACSI unduly and getting far more out of it than they are, but David assures me that it's mutual and not exploitative. But over the years, this relationship has grown and built a network of collaborations around these really interesting social issue questions that, quite frankly, I wouldn't have been able to even think of if I hadn't been working in this collaborative space.
Yeah, I suppose
So back to you, David.
Yeah, sorry. I suppose the thing that I'd like to end on is that, you know, if you look at this particular number of individuals involved, it seems like quite large, and you know there's a huge volume of people involved over the years. It's extended into other grants that Mike has alluded to, but I think the important part is that all these kind of collaborations across multiple successful grant proposals actually just stemmed from Mike having a question, wanting to get a better handle on it, wanting to develop some methods to give him a hand with it, and reaching out to someone in MACSI and then going for coffee. That turned into a summer master's project that turned into an IRC, and everything went from them. So I suppose what I would say is if anyone's interested in working with us, just reach out. Thanks very much.
Have you been able to predict any, let's say, dynamics, social dynamics that aren't evident historically, but that could be coming down the road that we should be prepared for?
Should I grab this one?
Yeah.
Yeah, great question. I had hoped that we would be able to predict things in that way. What I've realized is because it's a complex system, what we can do is map out trajectories and possibilities where things are more likely to happen and spaces where things are less likely to happen. So when we first came up with this network idea, with Padraig McCarran implemented it in a model, we analysed some American election survey data, and we could predict at that time, this was like 2018, fault lines that were very likely in American society, that if politicians saw this, they would be able to exploit it. And one was the issue of abortion, one was capital punishment, and I can't remember what the third one was. And lo and behold, within 2 years, the Republicans were making abortion a major issue, because I think it created a fault line between wealthy East and West Coast Democrats and the Democrats in the middle, who tend to be highly religious and African American or Latino. So yeah, the method does provide ways of mapping out the possible fault lines, but not a method of saying what's going to happen, if that makes sense. Yeah.
To ask a question that's emerged, I guess, since over the last couple of years, is agitators who are trying to seed an agenda. You know, so with the fuel protest last week, and it's all, or a couple of weeks ago, it's almost difficult to differentiate between what's a grassroots effort and what's the seeded, right-wing agitators, all this kind of stuff. I'm wondering if you ever, if through your data or through your research, you've been able to kind of come across that and almost work backwards to see where ideas and concepts originate from, and if they originate organically, or if they're almost seeded, bots, etc., etc.
Yeah, well, like naturally enough, if you look at any like online social media platform, you can not necessarily immediately see where information actually propagates from, but there are groups of individuals or botnets that would be set up to, find certain issues that would spark division and then work very hard on those. So, if you look at any kind of like online deliberative process and look at what's being shared, like things around the Irish marriage referendum, any American kind of election topic, you'd always see like online content being generated in such a way to try and amplify the divisions. So like it's what you can do is you can trace back and you end up seeing that typically those kind of accounts trying to like polarize both sides in such a way that the kind of middle gets drowned out effectively. So you kind of dichotomize the views of the other individuals in such a way that they're making them much more the other, I suppose.
Yeah, and I think the difficulty is that we don't have access to this data in real time. So I think there's a major social problem where public discourse is now on private platforms, and it makes it very difficult to work out what's even happening. So, for example, a lot of stuff is going through WhatsApp or Signal, Telegram, or private platforms where researchers don't even have access to the data. So there's literally no way of knowing in real time what's playing out. We can sometimes get access to the data in retrospect and then sort of slowly unpick what happened. But the systems at present are not set up in a way that allows us to figure out in real time what's going on, and I think that's a problem. Yeah. Thanks.
Thank you very much, David and Mike. And if there's time at the end, we might give you a chance to ask them some more things. So our next pairing is Kevin Moroney and Christy Sear. And I guess Kevin and Christy sort of epitomise the relationship between MACSI and SSPC. So SSPC is the Research Ireland Centre for Pharmaceuticals, and it's hosted here in UL. So if I introduce you to the pair quickly, Kevin Moroney is an associate professor in industrial and applied mathematics. So he sits in MACSI and in the Department of Mathematics and Statistics. Kevin's work really sits around applying mathematical modelling to industrial problems, which can vary from coffee brewing to pharmaceuticals, which you'll hear about today. And that kind of pairs very nicely with Christy's work. So Christy is a research program manager for targeted projects in SSPC. And what that really means is managing all of the challenges and complexity that come with multi-stakeholder projects across academia and industry, keeping us in line, I think, which is really essential. So I'll pass over to the pair now to tell you a little bit about what happens when maths meets pharma.
Thanks, Darren, and thanks for the opportunity to speak today. My job is actually very easy with this group, so don't have to worry about that. Hello, my name is Christy Sear, and as Darren said, I'm the Research Programme Manager in SSPC, focused on managing industry projects. And like Mike, I am an arts degree, so I'm glad to see we have a fellow traveller here. So just to start off, a little bit of background. Some of you may be familiar with the centre, but SSPC is a national research network that's really focused on delivering excellent science and training the next generation of researchers to deliver for the biopharma and pharma sectors. We started as a cluster, a research cluster, 18 years ago, and since then we've really built up a lot of capability as a national network, as I said. We have 9 university partners at the moment, 82 investigators, and we have supported 200 PhDs. And interestingly, over 1,000 publications, and more than 100 of those are with industry. So I know that there can often be an idea that there's a gap between academia and industry, but actually, in the spirit of true collaboration, it really does happen that, and in this collaboration specifically, there can be co-publication, so development of ideas. As I said, we're a distributed network nationally, so these are our investigators, and we're very proud to be hosted in the University of Limerick, but to partner with these excellent researchers in their own fields. 25% of them have recently been named in the top 2% of their field. So we range from preclinical work all the way through drug delivery and lifestyle extension. So you can see that we're hosted in the University of Limerick, but these are all of our academic partners that really create a depth and breadth of knowledge in the centre. And my role and my colleague Aisling Arthur, our role is really to help facilitate and matchmake a lot of those collaborations to make that science happen and that impact happen. So basically what happens in general is that Aisling and myself would get an ask from an industrial partner, and then we would look to our network, which includes MACSI, to identify the best expertise to tackle that problem. This ranges from fundamental research to very targeted short-term projects. So we would sponsor PhD students, also postdocs. Varda, I think we're coming into our third year, so fourth year. So it's moves from strength to strength. And Kevin will talk a little bit about that collaboration in a little while. But out of that expertise, we've been able to develop in the last 6 years 86 industry relevant projects, and these are just a little bit of the high level stats behind that. The breakdown of multinationals, SMEs, small to medium enterprises, and even startups. So we're really open to people who have ideas and sharing those ideas and making that research really impactful. And this is just a quote from Adrian Rodeka, who is the CSO, I want to say CFO, of our space industries. And I think that there's no better recommendation than straight from your collaborator, that we've really been able to achieve a lot in the time we've been working together. And we really just, as a program manager and someone who's not a maths background, one of the best parts of my job is to just be on the call with the team. And I find the curiosity and the exchange of ideas and the earnestness at which we're tackling these problems is really inspiring, because in my own background, I just really like working with people who have good ideas and working together to solve them. So I'll hand over to Kevin then.
Thanks very much, Christy. So hello, everyone. So I'm going to tell you a little bit about, well, why should we collaborate in the first place between MACSI and SSPC, and then my own story in that collaboration. So why collaborate? I guess in the pharmaceutical industry, there's been a big change, and there's a much bigger focus on model-driven innovation. So that can be driven by statistics, or it can be driven by more physical modeling. So I guess three of the main reasons for that are to accelerate the development and innovation, so to speed up how quickly you get to your best process or best product. You want to try and design in features into the process before they go wrong. Okay, so you simulate a production line before you make it, and that maybe allows you to get it right first time, or maybe second time, instead of having problems later. And then basically make informed decisions. So can you project problems that will come in the future? If you're controlling a processing line, can you do some kind of predictive control instead of traditional reactive control? And if you want to do that, you need physical models to enable it, and you need some kind of, I guess, control engineering or statistical abilities to make that possible. So really, the reason is we need multidisciplinary teams to tackle these problems. You need expertise and equipment. Often the industry partner has some of these features, but they may not have all. So if it's a smaller company, they may not have a modeling team, they may only have a small statistical team, or there's specialized equipment that SSPC may offer. So from the side of MACSI, we have technical expertise in data-driven modeling and physical-driven modeling that we can feed in. And then by linking to SSPC, we get access to lots of interesting problems. And because SSPC are aware of our expertise, they can call us when needed, essentially. And then what does SSPC offer to us? Well, a huge amount. I think Christy showed you how big SSPC is and how much expertise they have. So there's the center effect, I guess. There's lots of experts we can connect with, ask questions of, maybe call in, and people are very helpful with that, to give us subject matter expertise that we don't have. We're experts in modeling, but not a specific chemistry. The equipment, I guess, so we can build models, but we need to inform the models from real physics or chemistry. We need to also test them and validate them. Otherwise, if we can't validate them against data, well, they can't be used. And then in terms of supports, Christy and Aisling give us lots of support initially in recruiting people, communication, navigating IP, and so on. So my own story, I guess I've worked quite a lot with SSPC. Initially, I did my PhD, same time as David, actually, and came from UCC as well. Skip that part here. And I did my PhD in 2 projects with 2 industry partners. One was Philips, which was on modeling coffee extraction, and one was Johnson & Johnson's Vision Care, and that was a problem on cleaning contact lenses. And then I moved to SSPC, and SSPC give lots of opportunities. This picture is from a public science event, so it's another strength of SSPC EPE, where we did an event on, I guess, understanding the science of coffee. And you'll see David featured there as well, looking much younger. But that project really taught me a lot about collaboration. We worked with Janssen Pharmaceuticals, and it was in a big team of experimentalists. So that was an interesting project. It was on manufacturing of tablets, basically, and Aisling was the person who made it all happen there and made sure that we could navigate monthly update meetings, which I wasn't used to, presenting every single month. And then all the issues we had with co-publications. So co-publications are great, but with the big companies, they have to go through legal issues and so on. And thanks to Aisling and Christy now in the current project, we don't really have to deal with that, which is great. And the other thing I learned, I guess, is flexibility. So my background is on physical modelling, but I found in a team of experimentalists, there was lots of gaps in statistical knowledge and experimental design, so I had to learn some of that, which I've forgotten again. But it just shows once you have a degree in maths, you can be flexible in terms of how quickly you can learn things. I then went on to a short postdoc in 2020. I went back to modelling chemical dissolution. So coffee is chemical dissolution, so is drug release. So I was modelling dissolution from tablets there. And part of that, again, the strength of working with SSPC, collaborations in Rutgers University in New Jersey. So I visited there for a month. So the picture you see here is in the middle of New Brunswick. And I didn't know before I went, but apparently it's a twin city with Limerick. So as I was walking one evening, I realised that. So then, like David, came back into the department, MACSI again. But I didn't leave SSPC for too long because due to the connections, this project came from Varda Space Industries, and then I became a funded investigator in the centre again. So very briefly, what is the Varda project about? Because it's a very interesting project. So this company is based on the idea of manufacturing in space. So they want to have commercial space infrastructure to facilitate manufacturing in microgravity for things that can't be done easily in gravity. So again, here, the picture here is from their facility in Los Angeles, and this is their capsule that they put into space with whatever experiments they're going to do. And one of their ideas is that they're going to manufacture pharmaceuticals in space. And in particular, they're going to crystallize certain drugs that would not be possible to crystallize in gravity, but may, they hope, be possible to do in microgravity. Why might that be? Well, crystallization is where you get a crystal, which could be a drug crystal, appearing out of a solution. Once that crystal forms, it's typically denser than the solution, so it's sediments. And the solution also has different densities, so you get flow. But if you're in microgravity, it just crystallizes and sits there. There's no gravity to make it sediment, and there's also no gravity to make flow happen. So it's just a more controlled environment in which to grow crystals, and you may get different crystal structures that you could not get on Earth, which may be important for medical application. Why do they need modelling? Well, I don't need to tell you, it would be very expensive to send up lots of experiments into space and get them wrong. So again, the challenge here is to try and get it right first time or second time, or do the most relevant experiment to get the best data. So Varda have already done a couple of missions, and we hope soon they'll do a crystallization experiment, which we can check our models against. This project really wouldn't have been possible without the existing collaboration with SSPC. So initially the project, Varda identified SSPC because they saw a publication, not from us, but from someone else. Then they came to the centre. Then there was connections made. So Christy and Ashley reached out to us. So myself, Michael Vinicky and Darren were all in the project. We wrote an application with Varda. 1 minute, okay. We got, I guess, the right project, and then we also got co-funding. So again, the advantage of being with SSPC, industry have to provide some money, but SSPC can also match it. That allowed us to hire postdoc Milton, who's done lots of great work on the project. And then the other important part is the industry partner. So Varda, we found are very enthusiastic, very engaged, very open to new ideas, which isn't always the case. So they understand the scientific process, and certainly Adrian, who was our initial contact, is a great collaborator. The right support then, so Christy has been brilliant. So managing communication, approval of presentations, publications, which we don't have to do if we're not working with industry, but now we have to think about, maybe last minute sometimes, monthly meetings, contracts, HR. And then if you have these things right, success breeds success. So we were initially funded for 15 months. That was extended by another 2 years. And then finally, to finish up, so what are some of the challenges we had? The first challenge I had in my postdoc was the amount of acronyms. So day one, I had 2 pages of acronyms. There's no shortcut. They just give you acronyms, and then you take them down and you Google them and you find out hopefully what they mean. You need a plan, but you also need backup plans because things typically don't work as you expect. Why not? Data access, quality, experiments don't work, models don't work. The plan has them all working together, but you also need them to work on their own in case things go wrong. Expectations change, industry priority change, design changes, so you have to be flexible, publication IP. And then to close off, if you have the right team, I think you can address all of these challenges, or most of them at least. And then I guess the advantage is you can work on problems you could have never done on your own. So I'm going to finish up there, maybe a bit over time.
Thanks for the talk. Just interested to know, you mentioned there's some missions now and data possibly coming, or has it come already, or you're waiting on it?
So Varda have done some experiments in hypergravity. Hypergravity is easier than microgravity because you can do that on a rotating arm. So they have a big arm rotating. They can do 1G, normal gravity, 3G, 5G. So we have that data. Now, they've had a lot of issues getting high-quality data, so anyone in chemistry will know crystallization experiments are hard anyway, and when you put them in a rotating arm, to get replicable data is difficult. And then the in-space data, they've done 2 missions. One of them was a melt-cooled crystallization. We haven't been modelling that particular type of crystallization, but we are hopeful one of the next missions will do what's called an anti-solvent crystallization, which we are modelling. So not yet, but hopefully we're getting there.
I can imagine there's a nervousness that goes with waiting to see if what you've predicted from your model will be borne out by the data.
Yeah, absolutely. But I think for Varda as well, there's nervousness that their satellite will actually come back to Earth. So I think it's a bigger one for them than us.
Thank you very much, Kevin and Christy. So our third pairing is Bjorn Glaser and Michael Finnicky. Bjorn has kindly come all the way from Stockholm with his lovely daughters. And I suppose if the SSPC collaboration to some extent is a gateway to connecting to industry, the collaboration with Bjorn, you may see, is to some extent, as well as introducing interesting and exciting science, gateway to Europe. So again, I'll introduce you to the pair. Michael Finnicky is a professor in applied maths in the Department of Mathematics and Statistics here in UL. Michael's primary research, similar to Kevin's, is in deterministic mathematical modelling for modelling real-world processes, including industrial ones. So that includes things like electrochemical engineering and materials processing. And that has brought him in contact with Bjorn. So Bjorn Glaser is a professor of experimental kinetics in metallurgy at KTH Stockholm. And Bjorn leads a unit that studies the transformation of raw materials into useful products. And so the achievements there include analysing and optimising metallurgical processes with a view to improving efficiency, reducing energy consumption, reducing CO2 production. So again, I'll pass over to the two now to tell you about their collaboration.
So, first of all, thank you very much for giving me the opportunity to be here today. It was very nice traveling here, very nice being back in Ireland. Many years ago, I think it was 25 years ago, I studied in Ireland for a year in Carlow at this time, and I discussed it yesterday already. Ireland at this time was quite different. There was no big roads. It took from Carlow to Dublin 3 hours by bus, so it was a very interesting time, I have to say. So Ireland has changed a lot, I have to say. So Michael came up with the name metallomatics. I think he will say something himself, what he thought about that. But I will start with giving a short introduction to me. Even I was shortly introduced already. So as said, I'm a professor at KTH University. I became a full professor last year in 2025. Being at KTH now since 16 years, came there basically for starting a master program, continued then as a PhD student and going whole up climbed the ladder up to the professor basically. I'm also an adjunct professor at Limerick since 2025, and as said already, I'm a metallurgist. I work with metallurgy processes. So the industry, which basically has one of the biggest impacts on our world in general. So there are not so many steel plants in Ireland, basically. So I don't think any of you have even been visiting a steel plant. So when people asking me, how is a steel plant, how are the processes, then I said, always tell the story. When I was a PhD student, I was in a very small steel plants in the mountain of France, and we did industrial trials overnight there. And I was sitting there a little bit sleepy, and then I was waking up and I was thinking it was hot, it was loud, everywhere fire was splashing, and then I thought, that must be close to hell here, yeah? So that is basically what the steel industry is. And I say always to my students, either you like it or you hate it. There's nothing in between, yeah? So I have been finally ending up in the steel industry, and I doing high temperature experimental work with the steel industry since many, many years. So this is my subject I really like to work with, but I have been over the years also doing developing models for process optimization, did some CFD modeling and so on. So, but now you may asking the question, how does MACSI come together actually with this kind of heavy industries and my profession? And the thing is, as I said, we work with industrial processes. They are basically very difficult to control, very difficult to measure as well. So there are no sensors available at these harsh conditions, at these temperatures. And that is basically where mathematics is a very, very helpful tool, basically, to help us to look into processes, to optimize the process, basically to have the possibility to calculate, to get a better understanding what is inside the process. Yeah. Yeah, there while you had a lot of time to read what's on the slide, basically, while listening to me, so I will not go too much in detail to that. I think I'm passing on to Michael for a moment, and then I'm getting back to some examples.
Well, I shamelessly borrowed Björn's slide structure here, so which actually saved me a couple of hours. So I'll just briefly explain about myself. So my PhD now seems to be getting further and further back in the past with every year that comes, was actually in mathematical modeling of heat and mass transfer in welding processes. So that was maybe the sign of things to come further down the line. And then what I've done subsequently after that, has been to focus on industrial and applied mathematical modeling over a wider variety of applications. So Björn had this diagram in the middle, which I say I borrowed for his deep learning approach. So I called it deeper learning, but what I'm trying to mean by that is not to say that he is shallow, but rather that it's focusing on maybe traditional applied mathematical methods, so asymptotic methods, but then also combining that with numerical methods, but then also modeling as well so essentially it's all these three coupled together give us a way forward to the things that we model. And well, over the years, so on the left-hand side of this neural network-like slide, there's all the things which are not related to materials, which I've looked at, so topics with renewable energy and more recently the pharmaceutical industry, but then on the right-hand side, that is the materials. So various aspects of processing materials, so brazing of silicon or alloy or silicon alloys, continuous casting, and so on. But after that PhD, so did have an earlier spell in Sweden, which is where this interest in metals and materials came forward. there was a competence center at the time called the Faxean Laboratory. People who've done fluid mechanics may have heard of Faxean, but I imagine probably no one in this room has. Okay, but the idea was you have fluid mechanics at the center, but then supporting the other industries of importance to Sweden. And one of them did happen to be the materials processing industry, and that would have been the first time when I walked into Björn's department, but he certainly wasn't there yet, because that was 1999, I think. We can go on actually to how we've collaborated. To be honest, it's just KTH brings the problems and then we solve them, or do our best to solve them. Now, although MACSI has been around a long time, I think this collaboration with Björn is maybe the first time where MACSI has actually got an EU presence in large industrial European consortia. I think it's fair to say that, although we may have had other EU funding, maybe from Marie Curie before. The benefits, these are the next ones. These are Björn's words, not mine. So it's not just me telling you what the benefits for KTH are here. Advanced access to our advanced expertise, although they model there themselves. We probably, because we focus only on modeling, whereas in their minds they're having to do a bit of modeling, but then focus a lot on building the experiments and so on. We seem to solve the problem fairly quickly, apparently. Transfer of knowledge, international network, and strong partnerships. And the way we started was actually with the first initial communication was more on the applied math side, but actually as time has gone on, we realized that it's the statistics and the data science which ultimately may help more, but I don't hog this, so I try to open up to the statistics people to do that. I think what has helped is that because MACSI has had his long experience of solving industrial problems and transferring knowledge, for example, via the study groups, I think we have we may be quite streetwise as to what is actually needed, and then maybe it has also helped here that I had a past background in the materials area to help us hit the ground running. So I'll stop there, and Björn will actually then give us some concrete examples of the things that we've done. Yeah.
So basically, our collaboration started more or less, or took really off when we, from KTH, actually, we are introduced through Michael to the study group, and Michael explained that in one of our meetings at KTH, because he is also an affiliated professor at my unit, actually, at KTH. So he explained, we have the study groups, and we need some problems, and something like that. And then something popped suddenly up in my head and said, we're having there something where we could actually need your help. And then we came here together with my student, Sudan Shu. We came here basically got our problem reviewed and solved partly as well from I think 10 to 15 mathematicians at the same time for 1 week, which was very amazing, I have to say, what we did there. And by talking there to the people and seeing what people do, I actually realized that the work MACSI does, it does very well fit together with actually all the problems occurring in industrial discussions and something like that. And I always explain that to many people when they're asking me why you have a collaboration with Limerick. And I said, I think these guys have a very unique profile, actually, which I not have seen in Sweden. It doesn't exist in Sweden that somebody actually combines math in that way together with physics and so on. So it's a perfect fit for our industrial process and the description of our industrial processes, basically. So that's how everything started. In collaboration with MACSI, but we had a project before already, Michael and me together, where we did some description of the blast furnace inside the blast furnace. So this was a EU-funded project, but Limerick was not involved. It was only Michael involved as a co-supervisor for the student there. So there we worked already since 2019 on this problem to solve it. The project finished off 2023. This is when we came to the study group in 2023, and there was all about scrap. How can we recognize scrap when it's picked up in the scrap yard? How we develop a software on that? How does the operators on the end basically know have they picked up the right scrap for the right steel recipe and so on? And we got a really good head start on the project here from the study group basically. But then it's also was another problem solving where we actually discussed how we can layer the scrap inside the pockets and on the later side inside the electric arc furnace to be molten in a most efficient way, time efficient, energy efficient, and also we can use the alloys on the end the best possible. And this was also in a collaboration with a EU project which was coordinated by me at this time, the High Yield project, and we finished this project now off in 2025, and it's amazing what we got out. So the industrial partners are actually really impressed how the results ended up here in this project, and thanks, I have to say, to MACSI and the study group here. We really pushed the boundaries here, and the industry want to continue on this problem with us as well here. And this is our ongoing project, the Metals project, where we have a collaboration. Limerick is a partner in the project here. It's also about scrap sorting. We're using new technology in LIPS technology actually to analyze the scrap once it's sorted. Limerick takes care of the huge amount of data generated there and tries to make sense out of them basically, and developing a model how we can basically improve that. And I got a sign now that my time is up. Otherwise I would tell you for another hour things which we have collaborated with, but I think thanks a lot for listening. Thank you.
Thank you both. Very interesting. Really interesting to hear how the collaboration developed over such a long time. And I suppose, in your view, would you have been able to have that collaboration if, Michael, you didn't have the prior connection outside of MACSI to KTH?
That's actually a very good question. Probably not, I have to say, because for us, without Michael, Limerick would not have been really visible, I have to say. Yeah, which is a pity because it's a great university. It's an amazing campus here, amazing people, what you're doing here. But I mean, Stockholm is far away and Sweden. And probably without Michael, we would not know about what people does here in MACSI, basically. Yes. That's sorry, they're more, I'm really happy that we have Michael and we made the connection actually. Yeah. Mm-hmm.
So our next pairing, switch gears a little bit. This is something I guess with more data around, hopefully. So our next pairing is James Sweeney and Patrick Pratt, who'll tell us about a project using statistics to improve batteries. So again, I'll introduce both. James Sweeney is a professor in statistics here in UL, again in MACSI and in the Department of Mathematics and Statistics. James's research is largely centered around geospatial statistical modeling. So modeling problems where there is some spatial element, and that includes things like water resources, availability of renewable energy across the country. And James right now is academic lead on this collaboration with Analog Devices. So Patrick Pratt is a senior principal engineer at Analog Devices, focusing on battery state of charge and state of health algorithms for emerging battery chemistries. And so they'll tell us now about this pairing and a little bit about the project.
So thanks very much for that, Darren. This is very much, I suppose, a learning type process, watching the earlier talks, and I suppose how I can improve my slides and maybe more description of the process. So in terms of how this came about, actually a lot of the credit is due to Darren, I would say, because Darren, when she came to UL first and has become increasingly involved in MACSI, came up with the idea of going and visiting other departments around the university, and dragged me over to the chemistry department, the Brunel Institute in particular, and introduced us to Hugh Gainey and Ty Kennedy. So Ty was interested in some experimental design stuff, which I'll touch on a little bit later, and Ty had contacts in Analog who were interested in looking at some aspects of statistical modelling in this space. So I suppose through MACSI we've ended up here, and I was introduced to Patrick. I'll pass over to Patrick and I'll come back around. Some context.
Good morning, folks. Thanks for the invite to give you an overview and share the a sample of our work. It's good to get away from the corporate world and experience academia again, if only briefly. So, okay, which one is forward now? There we go. There we go. Okay, so I'm just going to give you some context, background, and kind of give you a feel for the problems that we're trying to solve, and James then will give you an example of one possible avenue. So as we all know, we're living through an energy transition, and this is largely enabled by the exponential drop in the cost of lithium-ion technology. So there's the actual chemistry of the lithium cells themselves, but on top of that then is layered a whole battery management system. And part of that management system then, we have a family of algorithms, which I'll touch on and give you a sense of the type of problems that we're trying to solve. So there's here the main ones. There's the one, the state of charge. That's basically a measure of the energy or fuel, if you like, that's in the cell. And ultimately, if it's an electric vehicle, that will translate into the range, how far your car can travel. The temperature of the cell is very important, not just the surface temperature, but more importantly, the temperature at the core of the inside of the cell. Then the state of power of your cell, so it could be lots, it could be fully charged or partially charged, but how fast can you charge the cell? How fast can you discharge it? So having an algorithm to estimate the state of power is pertinent, important. And then the state of health. Is it a new cell? Is it near its end of life? What is the health of the cell? And then anomaly detection. Is the cell going to fail? So if you can predict if the cell is going to fail this afternoon or tomorrow or next week or next month, that's of crucial importance as well. Then we get to probably closer to the problems we're trying to solve. Fundamentally, it's one of modeling the dynamics of the cell, so you can get back right down to the physics of it. So you can get a physics-based model. So there's a whole set of partial differential equations that you can write down from first principles. Fundamentally, just to give you some intuition, picture you have your cell, it's an electric device, but it's electrochemical, and there's ions flowing backward and forwards from the positive and negative terminal. How would you model that? So that's where you need a physicist, a material scientist, somebody that's comfortable with electrochemistry, and ultimately good at computational physics. So there's a whole range of problems there that need to be solved. And there's a lot of investment, a lot of interest from the corporate world in getting expertise in that area. But then on the other side, but once you've got that physics-based model, okay, with modern data centers, you could offload that and let it execute and run and do your predictions. But that would be for something like how much life is left in your battery, remaining useful life. You could take a couple of days to calculate that offline. But then at another level, if you're interested in state of charge, you're looking for an output, calculation, an estimate more or less instantaneously. So that has to be done locally at the cell. So you can't offload the problem up to the cloud. You have to do it locally on the battery management system in your car, for example. So that has to be done at the edge. So they talk about estimation at the edge and edge AI. So finally, before I hand back to James, I'll just give you an example of maybe a slight touch on one of the problems, namely state of charge. So state of charge is how much energy, how much fuel is in your cell. You can't put a probe in and measure that directly. You have to infer it. So that's why we're kind of touching on statistics. So we're going to infer it from other measurables, namely voltage and temperature. So you can see there on the bottom left-hand corner, you have a symbol for the cell. You have a device to measure the voltage across it. You have a device to measure the current. So from current and voltage, you now have to work out how much charge is in my cell. So you have to use a piece of maths called a state observer, and out of that you get an estimate of your state of charge. So the state of charge is, there's two key components though. you need a cell model. And so we start from our physics-based model and we translate that out and make lots of simplifying assumptions. And we end up with one particular way you can do that is to come up with an equivalent circuit. So you think of, even though it's molecular and physical and chemistry in nature, you represent that as an electrical circuit. And then you can write down some fairly simple linearized equations from that. And then you have a very simplified model of your cell. And then the other key part of a state of charge estimator is something that will, from the model, it'll infer then what the actual state is. So basically, at this stage, you've got it down to kind of linear algebra and linear difference equations. So I'll probably leave it there and back to James.
Patrick has described the process very, very well in terms of the complexity behind it. And I suppose touching on Kevin's point earlier around you're introduced to acronyms, less so much acronyms in terms of working with Patrick and analog, but more a better understanding of why your phone battery might say you have 10% power, but it turns off. And sometimes it might say it has 1% power and it stays on for the rest of the day. So it's not an exact science in terms of how much charge is left in a battery. There's an algorithm there that's trying to infer it, given some noisy data. And if you look at the models that are used historically are these kind of very complex machine learning, deep learning architectures. So Bjorn and Michael did a really nice slide on that, where we might have a process that we can describe with like a really, really complex model, as Michael described himself. And what the challenge with these processes is typically they require an awful lot of compute time, a lot of memory. And if you're in a static situation where you can outsource this to cloud, that's not a problem. But if you want to run complex algorithms on low-end computational chips, and car manufacturers don't really want to pay for higher end chips, how can you kind of do that? And as Darren has mentioned, ostensibly I'm a geospatial statistician, but I kind of think of lots of different things as space. So we can think of longitude and latitude, or you can think of some of the parameters that Patrick mentioned, voltage, impedance. And you could think of these as kind of coordinates. And in that coordinate space, there might be a smooth surface that we're trying to describe. So we can have a really, really complex process that's kind of hard to interpret or explain, or we have something more of statistics focused, something called a Gaussian process, or multivariate normal distribution, for those of you who are more familiar with these statistical terms. And what we're trying to do with this, so this process, or Gaussian processes themselves, have all of the same problems and worse problems than the traditional deep learning architectures in terms of computation and memory, but there's been a lot of progress in the space to try and address those so that in such a way that they may supersede some of those alternative approaches now. So challenges are computation, and principally the challenge of that computation comes from if I want to predict something at a given location, and I have lots of data, I will use all of that data to try and predict at this given location. But maybe I don't need to use all of the data, I can just use the observations that are close to where I want to predict. And this is overlaps with battery design. So a different project involving Tide Kennedy and the Bernal is around how can you optimize the parameters of chemistry or battery synthesis. So what temperature should you cook a battery at? What mix of chemicals should you use? It's the exact same process could be used to describe that complex surface, and we can try and optimize over it. So I guess touching on that point slightly, so instead of using all of the data or all of the points where we have information to try and predict at a given location in this parameter space, what we do is we take the graph and we just cut out the data we don't need. So we try and focus on our nearest neighbours, and from a Gaussian process perspective, this is something leveraging something called the Vecchi approximation, where we just kind of focus on our nearest neighbours. There's huge improvements in terms of there's huge reductions in the time it takes to fit the models, the memory speed needed. Right, so again, to I suppose steal a few points from Kevin just on the collaboration. Well, so I really like working with Patrick because he's interested in the problem, as Kevin reported in terms of Varda. Recruitment is a major challenge. So these are complex problems that require very talented, mathematically capable PhD students, and they have lots of other alternatives or alternative employment options at the moment. And paperwork, which is not my forte, is a complete disaster. And I suppose you can touch on the rest, Patrick, if you want to.
Yeah, just very briefly. Yeah, I guess from our perspective, analog devices perspective, this was initiated because we were looking to recruit somebody to help us build up the suite of estimation algorithms. And we searched literally the whole world and couldn't find anybody. So then we decided we have to grow the talent ourselves. And that ultimately led to this research work. And hopefully we'll build a pipeline of postgrad students, because there's huge opportunities at the end of the pipe for them. So,
yeah, good. All right. Thank you very much.
Thank you. Really interesting presentation. Kind of a question for both of you. Do you think that models like these that allow you to predict maybe the speed or the rate at which a battery starts to lose its storage power, etc., do you think that having these types of models will help expedite or encourage companies to, or like if they can be translated to other materials, it'll give companies more confidence to move away maybe from lithium batteries and try some of these newer materials that are being developed, like by Hue and Teig, etc. Because with these models, it can give confidence in terms of how they'll perform.
Yeah, so thanks very much. Great question, Sarah. So I'll touch on it briefly in that there's definitely I'll pass over to Patrick, but there's definitely a big interest in analog in looking at different battery chemistries. And there's a concept in this space called transfer learning, where you try and build these complex models on the chemistries that you know, and then borrow some of that knowledge to a transfer learning approach to try and I suppose speed up the rate at which you generate new battery chemistries. I think that's...
Yeah, I can give you one tangible example. So the traditional lithium chemistry mix would have been lithium and then nickel, manganese and cobalt. And cobalt in particular is environmentally very unfriendly to extract. So a more modern mix is lithium ferrite phosphate. And ferrite is an abundant material and less environmentally hazardous. But the problem with that particular, when you start trying to model that particular chemistry, it's extraordinarily more difficult than the traditional one. So from a modeling point of view and an estimation point of view, it's orders of magnitude a much more difficult problem. And that's why we need just people with strong competency in maths to help us solve those problems.
Thank you for a very nice presentation. And the topic is actually very appealing for me. The question is, how many parameters in reality do we need to use to estimate the lying life of a battery? Are there too many of them?
That's a problem I look at every day for weeks, months and years at this stage. So I can give you a chapter and verse. So I can give you kind of a quantitative answer. So very quickly, when you break down the model, you can break it down into two principal problems. You have the static response of the model. So that's when there's no current flowing through it. The voltage will kind of relax and come to a steady state. So there's one model for that. And that's normally characterized by some kind of polynomial fit. So you could be talking maybe 20 or 30 parameters for that polynomial fit. And then the dynamic response, that's, again, as I alluded to in the talk, you kind of think of that as an equivalent circuit. So there's kind of resistors, capacitors, if you're familiar with the terminology. But they're ultimately, from a parameter set, you might be talking maybe 12, orders of 10. Not hundreds, kind of orders of 10. That's what you'd be talking about.
Thank you so much. Another question that it's coming to mind, it's we need to do some prediction in that case. Is that right? We need to just predict. We do not know the answer. We want to just estimate an answer and compare it to the reality. And that's my question. We are doing this all in our batteries, in our cell phones, and all the time we know exactly what is going to end up. So I want to know, is there any grand truths when you want to compare?
Yeah. So maybe the easiest example I could give is the state of charge one. So when we're testing the algorithm, validating it in the lab, we would have very high precision lab grade instrumentation to calculate the state of charge. So there's, you speak to your electrochemists and you say, how can I measure the state of charge, down to sub% level? And but you need high grade lab equipment. You need to be able to measure the current and the voltage to very high levels of accuracy. And from that then you can extract the ground truth state of charge. And then you can go away and you can run your algorithm on, less high grade, it's low grade instrumentation, if you like. And then you can see how well your algorithm deals with certain impairments. If there's lots of noise in your equipment or sensors, how good and how robust your algorithm is in living with those impairments.
Thank you so much.
Thank you very much, James and Patrick. So our fifth and final pairing is Romina Gaburo and Florian Fauché. So this is an interesting one because both are applied mathematicians and both specialize in inverse problems. So you might wonder then why they need to work together. So I think we'll hear a little bit about how collaboration is valuable, not just across fields, but also within a field. So I'll introduce both. Romina Gaburo is an associate professor in applied maths here in UL, so in MACSI and in the Department of Mathematics and Statistics. Florian has travelled from Bordeaux to be here. We're very grateful and gave a lovely technical seminar yesterday about his work and is back again today. So Florian is part of INRIA, which is France's National Institute for Research in Digital Science and Technology, and is part of the faculty at the University of Pau et de, again I practiced this, Pau et de Pays de la Dour. Is that acceptable? Okay, good. So on that success, I'll pass over to the pair.
Thank you, Darren, for the very nice introduction and for actually not destroying the drama, the end of the drama. So, so this is a collaboration with Floria and the larger group, actually, that started, I think we established that we met around 10 years ago. I think that's accurate. And this collaboration started when we met in Paris, not a bad place to meet. We give it to the French. And this was at the IHP, which is the Institut Henri Poincaré in Paris, which is a great place to establish international collaboration. It's along the line of, if you're familiar with the MSRI in Berkeley, so it's really a fantastic place to be. And it was great to have a MACSI representative at the Institute. At the time, there was a thematic semester on inverse problems, which is what I do and what Florian does, although we didn't know each other. And there was a bit of an excitement there also to be there because the director at the time was a Fields medalist, Cedric Villani, and the Fields medal is actually the highest recognition, the highest award that a mathematician can get is the equivalent to the Nobel Prize. So it was really exciting to be there. And so this talk is about how we use mathematics to do imaging, and this sort of relates to the previous talk about trying to see what's inside an object by doing measurements at the boundary on the accessible part. And so we call them mathematics inverse problems. So if we think about imaging, you can think about different type of imaging. I would think that we all, at some point in our life, undergo some CT scan or ultrasound scan. So if you think about medical imaging, and so what you're really doing, you are probing the material. Could be the human body, for example. I think it's the image is there on the left-hand side, with some field, with some energy. In this example, you have X-rays. X-rays penetrate your body, and they interact with your bones and muscles, and depending on the density. And so depending on the density, that will give you information about the state of your internal organs and the muscles. Like a miracle, you get this image that you see when you're there, and I'm not looking if I undergo something like that. So, but then you have this image. And so what's the miracle is actually mathematics, and it's actually merging people that do the analysis, and that would be me, and computational people like Florian. And then you also need the practitioner telling you actually you need to take the measurements in a certain way. That's something that's physically sound. You're not just doing mathematics for the sake of doing mathematics. You could also be interested in searching what's beneath your feet and try to get an image of the subsurface of the air. Again, you are probing the material. The material now is the subsurface, and with some excitement, you try to to prop some energy, and then you want to see that interaction with what's going on underneath. And again, you get an image. And so this is my little cartoon that you have the object there. Once again, it could be your battery that you were talking about earlier, and you make your measurements of voltages and currents. And actually, in inverse problems, we call that electrical impedance tomography. From your measurements, you try to get information of the conductivity or the state of charge. And the solution, it's actually a big word to try to say solution to an inverse problem. You try to do your best, because these problems are really a mess. They're very nonlinear. They're, we call it post, but I'm not going to get into that. So you need a lot of data, but also you need to know about how to treat the data. Okay? You might have heard about false negatives and false positives when you undergo a scan. And these are because you might have artifacts in the image. And this is what we call in mathematics ill-posedness. You might have a lot of images that fit the data. And so the mathematician actually will tell you, well, no, you didn't pose the problem in a good way. So that's why you're getting this false imaging. And so really, to try to tackle a problem like this, imaging and inverse problems, you need three ingredients. You need the practitioner, and you need the mathematician, and you need the computational person. So mathematicians, yes, but also mathematicians that look at different aspects of the same problem. And so what is the main challenge is to talk together. And this is what we started to do when we met there, and find a common language. And that was the challenge at the beginning. It's like Florian talking to me in French and me trying to answer in Italian, and that doesn't work. So you need to find a common language. English and mathematics. And so this brought together quite a lot of people, actually. So myself in MACSI here in Ireland, different countries also, and different time zones. And then Giovanni Alessandrini and Eva Sincis, they were my collaborators at the University of Trieste. And Florian at INRIA in France, and Martin de Hoop, who was the geophysicist there. So he was our practitioner, although he knows a lot of mathematics as well. But he was the one telling us, okay, no, you can't do measurement this way. That's insane. Nobody will do that. So this problem was about imaging the Earth. So we had the geophysicist, we had the computational person, and we had the mathematician, and then other mathematicians, because the problem was very hard. And so Martin, when we met there at some coffee break, he brought us together. He knew us both and started to say, well, I know there is this new technology, actually in Norway. So you have this vessel in the middle of the sea. This technology is called dual sensors, and they shoot air. They have guns underneath. They shoot air, so there's pressure waves going into the Earth, and they can measure also the velocity. And Florian started to say, well, yeah, there's some computations that we could do with that, but what's the model? Like, how are we going to model things? So I wrote there just a little bit. That's a partial differential equation. That's our model. It's called the Helmholtz equation or reduced wave equation. And so we modeled the problem together, and then what are these pressure waves and the velocity? And the mathematicians will say, well, these are Cauchy data. It might not mean anything to you, but these are Cauchy data to my PD. And so we cast this inverse problem in the way that we thought was what we call regularized. So it was sound. We can try to do the inversion, and we can try to see what's beneath the seabed. So this was the goal. Okay, so use these measurements, model them, and try to see. And I think with that, I'm going to leave the floor to Florian, and then I might just come back.
Thank you, Romina. So yeah, just to continue on this topic, the idea, as you said, is quite simple to understand, is that we have a wave that will propagate through your medium. So you will be able to measure this wave somehow. And from these measurements, you want to see what's inside. And here, indeed, the point of departure with Martin was to say, okay, we have this new type of devices. It brings us a different kind of information. How can we use it? Does it bring us anything? And what is actually a smart way to use it? Just to use a similar method at what was done before, because it's a different kind of information. And how can we adapt? How do we have to adapt? And it was extremely important to have everyone in the workflow, from mathematics to the application, to make something that makes sense. So these are the three main groups, the three main ideas to combine to do this work. First, the mathematical analysis to define the framework, what is the framework that actually makes sense. you need the numerical methods because you need to make simulations that are as accurate as possible, but also as faithful as what is the reality. So you need the physicist to be with you to say, exactly, this is stupid, or this does not make sense, this is impossible, and you have to respect the physical limitation. And in this case, for instance, it was this use of new devices, and as well as we have in all of inverse problems, which are non-intrusive, you don't have access to the body, for the human body, or to the Earth. So you have to be specific to partial data, meaning we only have access to data at the surface, and this is what you have to work with. This is something we cannot avoid. And as you started to mention, it's very important that we speak the same language, and I think it's something that I really liked in our collaborations with Romina and with even with MACSI. I think it's very interesting that we come from different sensitivities, and of course we have skills. We are all researchers, and we all have skills. And what I found in MACSI is that we are able to talk to different sensitivities. That was amazing, like really extremely important and like indispensable to make actually meaningful science that you have to discuss with a physicist, you have to discuss with a mathematician, with a numerician, with someone that does a simulation, with a computer scientist. And having the skill is not sufficient. You need to have the people that are willing to discuss, that are willing to share. And this is something I found at MACSI, and I found it extremely, like really wonderful. So I'm very happy to be here, which is my first time in Ireland. So it's really worth it. So I'm very, very glad. And yeah, so this is how we started to work all together. This is the idea for the reconstruction. How do we proceed? And the idea is fairly simple. Is that on the one hand we will produce simulation. So we simulate waves propagating. So we simulate the physics. And on the other hand we have the observation. And the simple idea is to say I want to have simulations that are as close as possible to the observation. So we want to match the observation with the simulations. And of course, as you imagine, however simple it looks, there is a lot of problem at every step of this algorithm. Starting from the observation, how do we get clean information? From the numerical simulation, how do we make something that is efficient, that is accurate, but also that is sufficiently fast? Because if it takes 1 week to do a simulation, it's not worth it. So we really have to combine all of these difficulties and to address all of these challenges, and that's why we can't do it alone. We can't do that alone. And yeah, just to highlight what was the novelty in what we brought, is that from these new devices, so at first you can say, okay, we just have new devices, we use this new data, and actually we show that with some thinking and using the mathematics, these new data, they offer a lot of possibilities, in particular in combining a new kind of waves and new kind of events in the Earth. You have, for instance, earthquake or control sources. And with this new sensor, we are able to combine all of this data. And that's what's very interesting, because as a physicist, they have, okay, we have a new sensor, can it be useful? And actually, from the mathematical point of view, we said, yes, it brings us to new opportunities. That's completely different to what we were able to do before. And just to highlight a brief experiment of what we can reach for reconstruction. So you see on these pictures, on a synthetic experiment, so on the top left, you have the true model, so assuming that we know, and you have first a layer of water, which is all blue, and then different layers, which are sediments, for instance. On the right, this is our initial guess. This is like what we think the Earth is. And you see that at the beginning, we don't know anything. We have a very wrong impression of what it should be. And after the reconstruction, so when we try to match simulation with the observation, this is what we can get on the bottom left. And it's actually fairly accurate, because we recognize the different structures, we recognize the appropriate color scale, which means the composition of the material. So it was very nice to us, this result, to say, okay, what we propose actually works in a realistic context. And then it even went to some extent to the industry in the end. So it was very nice to see that, to have the complete workflow from the mathematical analysis to the industrial applications. So what happened next? And so first in 2023, there was this wonderful semester that you organized at Isaac Newton Institute, which was great, and which allowed me to meet other people in MACSI. So that was also very interesting for me to start discussing, and I was very happy to meet them again here, actually. And I'll let you conclude.
Okay, well then, it's great, of course, to have you here, and it was great to have you back there in Cambridge. And in the meantime, actually, Florian got very good news. He got his ERC grant just I think it was the year after. I think, in fact, when you visited, you said, "Oh, I got to the interview," or something like that. So it's great, you got that. But Florian is also a named collaborator on my research grant, the Research Island. On sustainability, where we actually very much use the ideas of those images that you saw there applied to different imaging modalities. And there is also kind of some ongoing traffic back and forth of PhD students between us, but also between our collaborators. So that this is a great partnership also for moving PhDs and getting them to the whole internationalization, getting more expertise, looking at different point of views and looking at the same problem from different point of views. So this is it from me at least, and thank you very much.
So just maybe on the inverse problem, like you said, you're using inverse problem to understand what are the parameters if the wave is traveling, and try to understand what is the velocity and all this, try to track down. And you mentioned about the earthquakes, and will it be possible to also understand where it will be originating from using those equations or like the inverse problem? And second question would be, say, for example, you're working on the in pharma. Usually, I work in pharma, so I'm asking regarding that. That suppose you have a particle interaction between solids and liquids or something like that. Is it possible to track down the interaction when we have the particle size distribution of those kind using inverse problem, or the developments you have done?
Say again about the second one.
The second one, say you have particles and liquid. They're mixing well together.
Yeah.
And I know the distribution of those ones. If from that distribution of the particle, can I go back and track those interactions between the particles?
Well, if you can, I don't know, but it sounds like an inverse problem in the sense that you have the effect and you're looking at the cause. So you have the effect, they mix well, and then you're trying to find. So it sounds like, but it's a matter of. We said we're going to talk, right? And so we're going to sit down together and talk about that. It sounds like you're looking at the inverse problems. Whether it is doable, maybe. I don't know. The other one about the earthquake, maybe you want to...
So for the earthquake, you said the location of the earthquake, right? Yeah, so this definitely, yes. This we can precisely locate the location of an earthquake from the measurements of the waves. So there are a few stations around the globe, well, several stations around the globe that will measure the waves from the earthquakes. And from this, we can very accurately, actually, locate the origin of the earthquake. Of course, what we cannot do is predict when it will happen yet. Yeah. But although, maybe to complement on that, what we can do thanks to the numerical simulation is now, as soon as we know there is an earthquake, we can simulate in advance, okay, what will happen in the next hours, what will happen in the next days, and this is a first step, maybe.
Are you aware of any applications of the inverse method to social issues, social phenomena?
I am not, actually, no. Are you?
No, but it just seems like a problem that we face in social sciences, that we see the effect but don't know the cause. And so I know nothing about this, but yeah.
Maybe we can talk offline. Yeah.
Very nice to end on some potential future collaborations. I'm just going to steal a few minutes of your time to finish up, if that's okay. Firstly, just to maybe reflect very briefly, because I love this event, and I must say, even as someone who's supposed to know everything that's happening, I still learn a huge amount from hearing people stand up and talk about how they work together. And a couple of things struck me about commonalities. And one real thing I saw is that there's huge breadth, right, of people doing very different things, sometimes collaborating across huge divides. But there's also such depth that even two people working in the same field can find huge benefits from sharing their specific specialities within that field, which I think is kind of beautiful. And then across those variations, the thing that struck me is that the benefits and the challenges are real commonalities, right? So there's this huge benefit of being stimulated, of seeing things from a different perspective, of being opened up to new problems. And then there's over and over these same problems around learning to speak the same language, learning to understand how the other person thinks. And I just thought it was interesting that even when you go from the same field to different fields, it's the same ideas. And then I wanted to finish by saying thank you to our 10 speakers who have put a huge amount of work into putting together a coherent story. And we often say that talking for 10 minutes is much harder than talking for an hour, because in an hour you can afford to speak inefficiently, but in 10 minutes you have to really think. But a bigger thank you again to James McCormack. So I think I get a certain amount of credit just for being the one who's visible here. But actually the reason that this happened and that it all came together very nicely and that we had 5 well thought out pairs was really James. So thank you very much, James, and I'm sure you all will say. Okay, so I think we've a coffee break now. Anyone who's sticking around for the rest of the MACSI events, please aim to be back in the main building by 12. And thank you very much.